told that this object represents a ladder that's leaning against a corner that's frictionless. And what they've told us is that if this angle here is anything less than 70 degrees, then it's going to slip. So at exactly 70 degrees, that means that the ladder is experiencing the maximum static friction that it can possibly experience. And what we're trying to find here is what that coefficient of static friction is equal to. So this is definitely what we would call an equilibrium problem because, at least at the moment, all the forces and all the torques are balanced. And that's really the definition of equilibrium. If you have a situation where all of the forces add up to zero and all of the torques add up to zero, then that is an equilibrium situation. And when those two things are true, you have one of two possibilities. One, the object may be at rest, or two, it might be moving with a constant velocity or a constant angular velocity. And so I knew that this was in equilibrium because they basically told us it was at rest as long as this angle wasn't less than 70 degrees. So since this is clearly an object that we can't represent as a point because it has forces acting at different locations along it, I'm going to draw it as a long object. And that's really important if you're going to analyze torques, because you need to know exactly where the torques the forces are being applied in order to calculate torque. So let's think about the forces that are acting on this object. So clearly there's a friction force. In fact, that is maximum static friction because of the situation that it's in. Now the ground will also at that location exert a normal force. Don't forget that the ladder itself, the object itself, has weight, and that's going to be acting at the center of mass. We were told that that was equal to 445 newtons. And then finally, we have the wall itself. And since it's frictionless, it can't exert any sideways force. It can only exert a normal force. Normal means it's going to be perpendicular to the object, to the surface. I don't want to confuse us by calling that Fn. Maybe I'll just call this Fn1 and I'll call this Fn2. And we also have to figure out the locations that these forces are being applied. Obviously, these are being applied at the end. Since this is a uniform object, this is going to be applied halfway up the ladder. Maybe I'll use a different color for lengths. So this distance right here would be half of 6.1, which is 3.05 meters. We do have to do a little bit of trigonometry, however, to figure out exactly where this point is. Let's look back at this picture here. What they told us is that this distance right here is 3.05. Let me draw that in a triangle over here. So this is 3.05. However, we need to know essentially what the hypotenuse of this triangle is. So hypotenuses are unknown. We do know that this is 70 degrees. So since this is opposite the 70-degree angle, I'm going to use the sine function, which says sine of 70 equals opposite, which is 3.05, divided by hypotenuse. So using my calculator, make sure I'm in degrees mode and not radians. I'm going to take 3.05 and I'm going to divide by the sine of 70, and I'm getting 3.25 meters for the hypotenuse. So again, that means that this distance right here out to where that force is being applied is 3.25 meters. So now I can do a couple things here. I mean, one is that I could, if I wanted to, add up all the forces in the x direction. They have to equal 0. I could add up all the forces in the y direction. They have to equal 0. And I can also add up all of the torques. Technically, it would be in the z direction. They have to equal 0. I'm going to start with the torques because I'm just noticing that this force is at an angle, and so I'd have to find x and y components. So if I can solve this thing by doing torques, I'd rather do it that way. Now, one thing to remember about torques is your choice for your fulcrum, your point of rotation, is important in terms of simplifying the math. I'm going to put the fulcrum right here because when I do that, when I calculate the torque due to these two forces, and remember the formula for torque is Rf sine theta, each of these forces has an R of 0 because they're acting right at the axis of rotation. And so they're going to cancel out of the torque equation, which is good because I don't know what they are. By the way, you might ask, um, you know, why is there a choice for where I can put the fulcrum? And the answer is because this thing is not rotating. So literally, there is no point that it is actually rotating around. However, the fact that it's not rotating means that it's not rotating around any point. So you can pick any point and say that around that point, the net torque equals 0, and you should get a correct answer because it isn't rotating, and so therefore there is no point about which it's going to have a net torque other than 0. Okay, so let's get back to it, and let's do this net torque equation. So the first force I encounter, other than these two, is the weight itself at a distance of 3.05. So R is equal to 3.05. F is equal to 445. And then there is an angle here. We have to do the sine of that angle. And it turns out to be not 70, but the complement of 70, which is 20. So I'm going to do sine of 20. One other important thing is which way is this having a tendency to make it rotate? It would have a tendency to make it rotate this way, which is the clockwise direction. Normally, we consider that to be the negative direction. All right. Next force that I encounter is this normal force right here, and that would have a tendency to make it rotate counterclockwise, so that's going to be a positive torque. Its radius, how far it is from the axis of rotation, 3.25 meters. We don't know the value of the force. I'm just going to call it Fn2, and it's at a 90-degree angle to the plank. And again, maybe I should go back and explain how I knew that. It really is just because they said that the roller was frictionless. And so the roller, I kind of drew a corner. I should draw a roller here. The roller is only touching this at one point. And it's sort of on the outside edge of that roller. And only friction can exert a force parallel to an object. So the only other force that could be exerted is a normal force, which is perpendicular to the roller. And really, since the plank is tangent to the roller, the normal force is going to be perpendicular to the plank as well. Anyway, that's our equation. That has to add up to 0 because we know that this object isn't rotating. So that allows us to figure out this unknown of Fn2. So let's see what I get when I do that on my calculator. 3.05 times 445 times the sine of 20. And then I have to divide by 3.25, and I get an answer of 142.8. So Fn2 is equal to 142.8 newtons. Now, of course, that doesn't answer our question. And I should go back and say, how are we going to solve this? We're looking for the coefficient of static friction. And, the only formula we have that has coefficient of friction in it is friction equals coefficient of friction times normal force. So the only way to solve this problem is by finding the friction force and finding the normal force and, dividing the one by the other. So now we really have to find these two forces right here. And you can't do that by changing the location of the axis of rotation, because no matter where else we move it, we're going to have two unknowns at that location. So this is why we have to go back and analyze forces in the x direction and forces in the y direction. So that is going to require breaking up this normal force into its x and y components. I could really use another color pen here. Oh, I have a green one. Let's do that. So we're going to take a close look. And again, what I want to do is find the x and y components of this normal force here. Now, of course, one issue is finding an angle that it makes with things. So there we just start looking. I mean, I notice, we know that this is a 70-degree angle, and so up here, this would be a 70-degree angle as well. And then this is a 90-degree angle here, and this is a 90-degree angle here. So this is the other part of a 90-degree angle. So that makes this 20 degrees right there. And again, this is 90 degrees, so this makes 70 degrees there. And then ultimately, it looks like I'm coming to the conclusion that this is 20 degrees right there. Hopefully that geometry made sense to you, and I'm sure there's another way I could have figured it out, but that's sort of the way that I did it. So that means that, and it's just getting too messy in there, let me redraw this, that if I redraw this point right here, I have Fn2, which by the way we now know is equal to 142.8. And this is a 20-degree angle here. And so what I want to calculate, I'm going to drop it perpendicular to the x-axis. I want to calculate the x component. And likewise, I want to calculate the y component. And since the x component is adjacent to the 20-degree angle, I'm going to use cosine. So cosine of 20 equals adjacent divided by hypotenuse, which is 142.8. So the adjacent side is equal to 142.8 times the cosine of 20, which is 134.2 newtons. How about the opposite side? I'm going to use sine for that. Sine of 20 is equal to the opposite side times divided by 142.8. So opposite is equal to 142.8 times the sine of 20, and that's 48.8. Okay, so let's go back to our net force equations, and I'm going to have to do both because I have to figure out both the force of friction and the normal force. So it doesn't matter where I start. Let's start with the y direction. So really just looking at the forces, not torques, and looking at the y direction. Right here I have Fn1, and that points up, so it's positive. Here I have 445, the weight of the ladder. And then over in this diagram, I have the y component of Fn2, which I just figured out is 48.8. So those have to add up to 0 if this thing is actually at rest. So what do we get when we do that? We get 396. I'm going to round that off right there. So Fn1 is equal to 396 newtons. It's one of the numbers we're going to need. All right, let's add up the forces in the x direction to get the friction force. And so again, in my diagram here, I do have positive Fs max. The only other sideways force is this x component here, which is 134.2. They have to add up to 0 since it's in equilibrium, so friction definitely equals 134.2. Now, finally, we can figure out the coefficient of friction, which is the force of friction divided by normal force. 134.2 newtons divided by 396 newtons. And the coefficient of friction looks like it is 0.339.